Okay, what I'm wanting to do is go through several examples of using substitution and integration. Again, this is going to be something that's going to be fair game. I'll ask a couple light questions regarding it on the test, on the exam on Wednesday. But I do want you to be able to handle some basic constructs regarding it, okay? So I want to go through again something I talked about on Friday. One example, I'll do it briskly because I've already said this, but if you've got a situation like I'm gonna switch over to my iPad, but if you have a situation like you've got a chain rule situation where when you took the derivative of something, you've got a composition of functions, you've got to take that into account. And you've got to do the inside function and the outside function. So if you have the derivative, for instance, of sine of x cubed, notice that if I take the derivative of that, my y prime will be, I've got to take the derivative of the outside function, which is sine, which is cos, the derivative of sine is cos, and then you come back with that same function that was in there, and you got to multiply it by the derivative of the function that's within, which is the derivative of x cubed, which is 3x squared, okay? And we're going to get used to the idea of using the letter dx and using that, and we'll talk about that in terms of dy dx and a combination of ways of looking at it, but get used to using it. It's part of what's needed for a complete writing up of a solution using substitution. All right. So the circumstance is that if you have, if you're taking an integral and you've got this compilation of stuff together here, this same thing, you know, to recognize that, to go back the other way, what did I take the derivative of to get this? Chain rule, original function in there. So the idea would be, if I can recognize, remember what chain rule is, you got to take the derivative of part of the function. So if you can recognize that there's one piece of the function and there's a derivative of that function, or a constant multiple of that function, the constant multiple of the derivative of the function, then that's something to be looking at. So if I, in this situation, the substitution idea that I would introduce is, I've seen in some books, they even call it U substitution because the letter U is used a lot. I've seen other books use W and a combination, different letters, whatever. But if we set U equal to the number that's the term that's going to be taking the derivative of, okay, then if U equals x to the third, then the derivative of U, and one of the ways to look at it is derivative with respect to x, okay, is equal to 3x squared. And then if you solve for du, you get 3x squared dx. Get in the habit of, I usually don't write du dx, I just write du and get ready to be using the dx as one of the factors in the situation. But once we recognize that, now we go in and use substitution. So I've got my u is equal to x to the third. So now that I can rewrite this as the cos of u times my du is that 3x squared dx. And that simplifies all the conglomeration of factors, condenses down to just the substitution. It's a simple, what's the cosine of u? The integral of cosine of u, well, that came from sine of u. Now we're introducing the concept of plus c needs to be utilized. But then when we draw back into the, replace the substituted term, we started in x, it needs to turn an x, return it to x. So don't leave your answer in terms of u that you did the substitution with along the way. That was just a tool to help get through back to the substitution with, in terms of x. So we end up with, the sine of u, the sine of x cubed would be the solution. So when you start with this term right here, you know, that what you end up with is this simple thing that we had started with up there at the beginning. Okay, that's the key idea. And the substitution is in that fashion. Let's talk about a couple other problems that I'd like to work through that have to do, that are examples of this type of thing. So let's look at this other one. Let's now look at this one. I said a constant multiple of it. So if we have an integral of, check this out, we've got x times the square root of x squared plus 1 dx. Okay? What I said to look for was if you can see a term, and if you take the derivative of that term, another term that could be the derivative of that, or a constant multiple of the derivative. See, if I take the derivative of this, I get 2x. Well, I've got the x. A constant multiple of x, 2x and x are constant multiples of each other. So that will work, because now watch what I can do here, okay? So if I do a substitution, recognize the thing that I'm going to take the derivative of to get the other, u equals x squared plus 1, then the derivative of u is going to be 2x dx, okay? Now look, I've got the x dx. I need a factor of 2, just like we're able to do in other places in our algebraic manipulation, so to speak. If I want to multiply and stick a 2 out there, if I also stick a 1/2 out front, that counters it. The 1/2 and the 2 are two factors. Multiplied together, they give you 1. So you end up with this situation. Okay? So now I've got so I had to introduce the 1/2 out front in order to introduce the 2 that I need to use the chain rule on this, the internal term, right? So now I've got the 1/2 introduced, and if you want to rewrite this, you can see that this is equal to x squared plus 1 to the 1/2, and I can put the 2x dx together out here so I can see that that's my du specifically. So now if I do a substitution, I haven't integrated yet. I haven't done any integration, but now I'm just going to substitute. And this 2x dx is my du. So now the idea is, now I do the integration. So I've got 1/2, that's u to the 3/2, right? And divide by that new exponent. And the du and the integral sign go away, and I add the plus c. This is an indefinite integral, so that's happening. So now I'm dividing by a fraction, so if I flip and multiply, this ends up giving me, I've got 2/3 times 1/2 u to the 3/2 plus c. Now I'll simplify that, and also at the same time resubstitute back in my x squared plus 1 for u. So I end up with the 2's cancel here. I end up with 1/3 x squared plus 1 to the 3/2. So if you were concerned about getting it back into a radical form, then that would recognize that's the square root, 2's on the bottom and 3's on top. So we've got 3 in the denominator, and on top we've got x squared plus 1 with a root over it. It's a square root, so I don't need the 2, but I do need a 3 somewhere to indicate that it is a power of 3 plus c. Okay? So look what happened. And then it would be a matter of always being able to go back through just before you get to the radical, take the derivative of that and make sure the end result would be what you started with. You know what I'm saying? That would be a key thing to be doing. But that's the idea of introducing a constant multiple of the term. All right? Let's go do one more. I've got a couple more that I would like to look at here. And let's see here. One of them is right here. Okay, check this one out. This is kind of unique, I thought. 3x plus 2 dx. Okay, this is a unique situation on this one because there's no other term out here that's being multiplied, okay? But look if I'm considering, this is not just x, but if there was a chain rule, notice what would happen? I would have to take the derivative of the inside function, and that means a multiple of 3 is going to show up. So I've got to counterbalance that somehow. So the 3 is going to show up there, right? So that means if I have u equals 3x plus 2, then du is going to be 3 dx. Well, right now, all I have out there is just dx. I don't have a 3. So I need to introduce a 3. And if I introduce the 3, I have to also multiply by 1/3. So as a result now, I've got 1/3. Let me move this sine of 3x plus 2. And let me put the 3 dx out there together. I'll move that over there. And now I've got this, pardon my sign looking like a sign, sign. But anyway, I've got this now. And now I'm going to do the substitution. I've got my 3 dx over there. There's my du, and I can substitute. I had to introduce that 1/3 to counter the sign issue, the 3 that was going to show up in the chain rule. So now I'm going to do the substitution, and I've got sine of u du. That's it. So I introduced that 3, and now I've got everything condensed. So now what's the integral of sine? What did I take the derivative of sine to get sine? I mean, what did I take the derivative of to get sine? Well, it's cos, and this is the one where you got to switch the sign. Remember, it turns out to be negative. So we end up with, make sure you use parentheses on this, negative cos u, and this is going to be a plus c in this situation. So we end up with the minus sign, so I end up, and then I'm going to resubstitute in the u. So I've got a minus 1/3 cos u plus c. And stop and think, if I took the derivative of this right now, look what I would get. The derivative of cos is negative sine. The negative would cancel, and I'd get sine. And then I have to use the chain rule and get a 3, and that 3 is countered by this 1/3. They would cancel out, and you'd end up getting back to just the sine of what you started with, okay? So I want to just make sure you see that constant multiple thing is a real situation that does show up, okay? Let's do another one. This one's kind of interesting also, and I think it makes a point. I'll do this a couple different ones. The first one is integral of where it's got a numerator and denominator. Okay, and notice how they do the notation. They put the dx on top, all right? And that's going to be the same as if I move the dx out here, but it's the same. It's kind of like a multiplicative factor even being considered here. Notice what this is. The function that we would take the derivative of is on the bottom. Then you take the derivative and put it on top. Because we got a cube on the bottom in the denominator. Take the derivative, it lowers the power by 1, so it becomes squared. So it looks like our u is going to be on the bottom. And if you stop and think about this for a second, I will talk about that in just a second. I get 4x to the 3rd minus 1. Notice what du is. I get 12x squared, period, dx. The minus 1 this goes away. So I've got 5x squared. I need 12x squared. U is on the bottom. You now stop and think about it. Remember, does that sound familiar? When the u is on the bottom, you take the derivative of something that's on the bottom. 1 over x, natural log. Okay, so this is going to be a natural log situation. But watch this. Now I need 12x squared, and I got 5x squared. So that means I'm going to need 12. So if I can divide by 5 and multiply by 12, that'll give me the 12 on top, and the 5 will cancel. That'll give me the 12x squared. So if I need to multiply by 12/5, that means I have to multiply the outside by the reciprocal, which is 5/12, right? So that'll give me another, so now I've got 5/12. The 5's cancel. I've got 12x squared dx on top, and I've got 4x to the 3rd minus 1 on the bottom. I already got my dx is up in the numerator, okay? So now it is a matter of do the substitution. So we haven't changed anything yet. We haven't started integrating yet. The 5/12s had to be introduced. And now let's substitute. So u is on the bottom, and 12x squared dx is on top. So that's kind of like this. That's du. Hey, if ever you've got u's and x's together in there, something's wrong. When you do substitution, all of the x variables should be gone. If you've got a combination of them, it isn't complete yet. It's not ready. It needs to be done a little differently. So look what I've got now. I've got 1 over u du. Natural log of u is what that circumstance is. And I've had to introduce that 5/12 out front. Time to integrate. Integration bar goes away, du goes away. So now I've got 5/12 out front, and now I've got the natural log. And if you remember, we need absolute value signs around that natural log plus c. And that's all it was 1 over u. Therefore, it's just natural log of u. Got that. And that is now equal to 5/12 natural log of, what it was my u, 4x to the third minus 1 plus c. Yahtzee. Take the derivative of it. Notice what would happen. That the term in the parenthesis, in the absolute value signs would go to the denominator, and then you got to use the chain rule, and you'd get 12x squared, and then factor that out. The 12s cancel. You end up with 5. It just follow through with the process and work through it and go for it. One other one I want to do, I'm going to do up here as well. This one is kind of an interesting one. I think it's kind of a noteworthy. I'll tell you what, I'm going to do it on a fresh screen. Okay, so what's happening now is it's interesting because it's got to do with something in the denominator again. We got e to the square root of x over the square root of x dx. Okay, and it seems like, well, that square root of x needs to be up there with the dx if that's going to be part of it. Needs to be up there with it, and if it's going to be part of the derivative aspect of the situation. But check this out. This is a unique situation, and it's kind of important that once you see it, you'll know that it exists. But if I have u equals the square root of x, which is equal to x to the 1/2, right? Then du, check this out. Bring the 1/2 down front, and what do I have to do? I've got to subtract 1. That's going to be negative 1/2. Okay, dx. So now that negative 1/2 takes the x to the denominator, which gives me 1 over 2 square root of x dx. The x to the 1/2 had to go to the denominator. That's this. So the square root of x belongs, the derivative of the square root of x puts square root of x in the denominator. You get that negative exponent, the negative 1/2, to show up there. So we've got the square root of x in the bottom. We need a 2 down there. So we need a 2 down there. So if I put a 2 down with the square root of x, then I need to get a 2 out top in front. Okay? So now let's rewrite this in a format that will be visible here. And once you've seen it, it's something you can work with yourself. I'm going to write this as x to the 1/2. And then we're going to multiply that by 1 over 2 x to the 1/2 dx. All right? And that's what this is. That's what my du is. So I end up with now I'm going to do the substitution. I'm still got the integration bar is still needed, but now I've got e to the, that's my u, and this is my du. All that mess simplified down to just a basic eu to u, and when I integrate it, all the stuff goes away. But I had to introduce the 2 out front because of the chain rule. So now integrate. E to the u is e to the u. So I've got 2 e to the u plus c, which gives me 2 e to the square root of x plus c. Is that special? Okay? So that's the general idea. I wanted to introduce a variety of different things that could happen with that. And I'm going to include some sort of that on the test on Wednesday, okay? So take a look at these. If you want to review them again, feel free. But it's a interesting little arrangement. And in Calc 2, you use it all over the place. It's abundant. It's rare that you don't have to use substitution, as a matter of fact. But thank you. And take a look at it and get ready for the test on Wednesday.